Okay, so hi everyone. In tonight's lecture, what we're going to do is we're going to start with a fairly small lecture first, just on pyramids, and this should only take us maybe 15-20 minutes, and then we'll move on to SIFT, which I'll do as a separate recording, which is scale invariant feature transform. So we'll look at that next, and that'll probably take us over an hour to do, maybe even a bit, maybe up to an hour and a half. So we'll probably be spending the 2 hours tonight overall, but we'll try and go through it as briskly as possible. So we're going to start with a little thing called pyramids, which are one of the constituents that's used in SIFT, but it's used elsewhere as well, and it's an important concept. I had originally slated in for something that was going to happen in the first two lectures. But I felt that it was just one of those things that when I wanted to get on to some of the other multiple views stuff, that I wasn't really going to get a chance to go into it in any great detail. So I left it back until now, along with SIFT, so that we could kind of look at some more significant detectors. So when we talk about pyramids, we're talking about scale, and the whole idea here is that we want to look at images, and we want to look at them at different scales. So we want to look at things at different scales so that we can try and find objects or features within them that show up at different scales. Okay, so one of the common problems with finding objects or features in images is that of scale. Humans are good at recognizing the same type of object no matter what its scale is. So if you look at an image and you see a car in an image, it really doesn't matter whether it takes up most of the image or it's only if there's a load of small cars in the image, you'll normally be able to tell that that's a car. And humans are very, very good at that, but computers are not. So what we need is a system whereby we can search images at several different scales so that we're looking for the same thing, and if we just rescale the image, then it should appear the same. So this is the idea we'll look at today, and it involves a construct called a pyramid. So here's the idea of a pyramid here, where we start with our full resolution image down the bottom here, which is that one there. So that's our full resolution image, and the full resolution image then is resized down to smaller. Okay, so you resize it down to smaller then for your next level, and then smaller again, and then smaller again. Okay, and you keep going in that way. So normally the levels in the pyramid would go down by half each time. So the idea is they go down by half in each of X and Y, and by doing that then you would end up with quarter the number of pixels in each case as you go up, because you've gone down by half in each case. So a pyramid is built by creating multiple copies of an image at different resolutions. Each level of the pyramid is 1/4 the size in area of the image at the level below it, i.e. it's halved in both X and Y. So the lowest level of the pyramid has the highest resolution, and the highest level has the lowest resolution. Okay, so when we get up to this, you can see there's only 1 pixel here, obviously, but when we get up to the, and we normally wouldn't go down to just 1 pixel, by the way, there'd be very little point in that. But as we go up in levels of the pyramid, we're basically going down in resolution. We're able to see much less information. Now, it may seem that downsizing an image is a fairly straightforward job, okay? But it really isn't, okay? So the problem here is one that I cover a lot in digital signal processing, but it's not maybe something that many of you might be familiar with. So it's known as the Shannon-Nyquist theorem. How many of you are familiar with that? We've only got a few in tonight. So Maurice, I expect that you're familiar with it, but Vin and Colin may not be. Yeah, so Vin isn't, and Carl is saying it two times. So yeah, so it's related to the where you have to sample at twice the highest frequency content that's in your signal. Okay, so if you've previously taken a class in DSP or data communications, you may be familiar with the Shannon-Nyquist sampling theorem. So this is Claude Shannon and Harry Nyquist, and Claude Shannon in particular was very prolific in computing and in signal processing back in the kind of the 1940s and 1950s. So this theorem states that the sampling rate must be at least twice the highest frequency. Now, strictly speaking, it goes a little bit more. It's to do with bandwidth, but that'll do for our simplistic explanation of it here. Now, the problem is, if we downsample an image, what we're basically doing is we're dropping our sampling frequency by half in each direction, but we need to only consider that we're dropping it by half in one direction. So when we do that, the problem is if we have frequencies that were higher than that were higher than a quarter of the original sampling frequency, then they are now going to be bigger than half of the new sampling frequency, and that's a problem. So if we downsample, i.e. set the sampling frequency half its current value, then we need to ensure that there is nothing in our signal, which is the image in this case, that is higher than half of the new sampling frequency. Half the sampling rate is called the Nyquist rate, or the Nyquist frequency, obviously after Harry Nyquist. So Maurice, I don't know whether you remember or not, because it's a while since you did it, but we did a lot of multi-rate data techniques in digital signal processing in the level 8. And in those circumstances, what you would do is you would sometimes decimate a signal. And before you did it, so you could interpolate or you could decimate. And when we were bringing it down in its number of samples, so if we were, let's say, halving the number of samples, one of the things we had to do first was we had to low pass filter it so that we removed any frequencies that would now be between the new half the sampling frequency, or the new Nyquist frequency, and the sampling frequency. They had to be removed before we did our downsampling. And the same happens in an image. So if we don't, we get a thing called aliasing, which is something that happens when you just sample in the first place, if you're sampling an analog signal. But if you already have a digital signal and you downsample in some way, then you will have the exact same effect occur. So this phenomenon is called a phenomenon called aliasing will occur. This is where the frequencies above the Nyquist frequency aliase or appear to be frequencies below the Nyquist frequency. In images, this normally takes the form of moire. So this is the sort of thing you see when somebody turns up with a striped shirt on a TV program, and it looks like it's almost electric because it's actually showing up as different frequencies than it should be. Aliasing itself, probably the easiest explanation that everybody is familiar with, is actually not sampling in the spatial domain, but sampling in the time domain. So when a film camera is filming, it's normally filming at about 24 frames per second, and that's not a very high frame rate. So if something is moving in the image faster than half of that, we get a problem in that it appears to be doing something else. So where you really see this is in cars, or particularly in the old westerns where you see a stagecoach moving. You would see the wheel of the stagecoach moving, and then it seems to start moving faster and faster, but then all of a sudden it slows down again and starts moving in the opposite direction and then going back and forth. And that's that aliasing effect. It appears to be doing something different than what it is doing. I don't want to go majorly into digital signal processing. It's a completely different module that I teach, but it is just important to be aware that these effects are very, very real, and that there's not just a simple way around them. You can't just ignore them. So we're going to have to smooth or you do a low pass filtering on this, and of course we can do that with a Gaussian. So what we must do is low pass filter the signal or the image to remove the frequencies between the new Nyquist rate and the old. We can do this in an image with our good friend the Gaussian. Now you obviously have to choose an appropriate Gaussian in order to do this. So we'll have to choose the size of Gaussian carefully so as not to remove any more than we should need to remove. Because obviously you don't just want to go blitz it and completely smooth it out and remove frequencies that we're not going to aliase. So the Gaussian there is important, and the size of it is important. So what we do with our what we'll call a Gaussian pyramid. So this is a pyramid where we're going to make each of the images, but we're also going to Gaussian smooth before we do each of our downsampling of our images. So in a Gaussian pyramid, the lowest level, which we call G0, is the original image, and this is L. This is capital L. I really need to try and find a way around this. So this is capital L, which is not the same as what I come up with here. Sorry, I've made it confuse myself. This is I, capital I, for my original image, and then down here we have a little l, which is the lowercase l. Okay, so just be careful of that when you see it, that you don't get confused between them. So L stands for level, and the I is obviously for our image. So the next level up is G1, and it's computed by a Gaussian, or a discrete approximation of a Gaussian, which is a weighted average of the values of G0, which is the one below it. So each level, which we call GL, is therefore computed by a Gaussian weighted average of the values of GL minus 1. So the idea there being that G1 is computed from G0. So if we use something like a 5x5 Gaussian, this would be as follows, where you go from -2 to +2, including 0 in between. You go in both directions, and that's our weighting function there, our Gaussian. And what we do is we use the previous layer in order to calculate the current layer. And we have a 2 in here in each case. And what that's basically saying is we jump to every second pixel as we go. So what we're effectively doing here is we're both smoothing and doing our downsizing at the same time, okay, which is perfectly fine. Now I know, strictly speaking, the smoothing must be done before the downsizing, but as we do it here, that's perfectly fine in doing it in this manner. So the other point to make about the Gaussian is that, of course, it can be made separable, and that's great because it means that we can compute these things a good deal quicker than we would do otherwise. So what that basically means is that you can downsize in one direction. You'll end up with a kind of a rectangular image first of all, and then when you downsize that rectangle in the other direction, you end up with a square again. So that's how we get down to that. So the 2i and the 2j has the effect of reducing the image by half in each direction. Now there is another version of this, which is where we expand the pyramid. So where we start with a level of the pyramid and we try to recreate a bigger version of it, which is the term Morris put up there a few minutes ago, interpolating. This is effectively the same as that, where we're basically making an image double its size. Okay. Now the thing is here, firstly, you might think, well, if we make an image double its size, what's the point of doing that? Because we're not really creating any new information, and you can resize images bigger. But the other thing is that if we were already just downsizing, why would we want to upsize? So the whole point here in many cases is that we sometimes want to subtract two images from each other, one which has been downsized and the other which so one which has been downsized first and then re-upsized, where it's lost some of its information. Okay, and we'll see in a moment where that would come up. So related to this is the idea of expanding an image from low resolution to higher resolution. If we want to do this, the formula is very similar with only a few key differences. So you can see them there. Again, this is for a 5x5. If it's a 7x7 Gaussian, you would basically just use, you go from -3 up to +3, and your W function again here is just your Gaussian in two dimensions. You can see here that what we're doing here now is we're dividing by 2. So this is kind of subsampling between pixels. So the major difference is that we're dividing by 2 now instead of multiplying by 2, and this will have the effect of subsampling, i.e. we'll end up with twice as many pixels as before in both x and y. We won't end up with more information, okay, so you can't create something from nothing, but nonetheless we will make an image that's a little bit bigger. Now what's maybe not as obvious here is the... just was I going to mention it here, one of the reasons... oh yeah, we'll come to it in a minute. So these are, I'll come back to that, what the point I was going to make in a minute. So these are normally carried out with the standard Gaussian, which is, so the Gaussian pyramid is normally carried out with the standard Gaussian reduce pyramid, which is why we see the indices L and N. We're using the reduced layer to recreate a different version of the high resolution layer, okay? So why we do that, well, we'll talk more about that later, and we'll see that a lot in the SIFT lecture later. But here's what I was going to mention there a minute ago. Do we need to use a Gaussian for upscaling? Couldn't we just make every pixel twice or something like that? Okay, so there's two issues here. Firstly, the Gaussian works well as an interpolation method, and what I mean by interpolation is that if we have two values, let's say I have a value 5 and I have a value of 7. So let's say, for example, at 2 different hours of the day, let's check at 2 o'clock and the temperature is 5 degrees, and at 4 o'clock I check and it's 7 degrees. What was the temperature at 3 o'clock in between? Okay, so this would be, if we use simple straight line interpolation, we would say that it would have been 6 degrees. But there are, of course, lots of other types of interpolation that maybe try and take other things into account. We don't know that there wasn't a sudden drop in temperature down to 3 degrees and then back up to 7 in between our samples. So we can't recreate what we don't know about, but we can make a reasonable assumption about what was in between. And it turns out that in terms of a two-dimensional image, using a Gaussian is actually a fairly good way of smoothing out the differences between two values, in between different values, in order to figure out what should be the new values in between them. So that's the first reason we use a Gaussian. Secondly, and again, I'm not going to go into it in too much detailing, generally when you're upscaling, you do need to low pass to remove aliased frequencies, although this is not as obvious and a little beyond the scope of these lectures. So the thing is that when you're doing this interpolation, again in signal processing, if you decide to suddenly, you take a signal and you try to make twice as many samples from it, what will happen is you now have a new sampling frequency. Half of that sampling frequency is now a much higher value, and therefore the original signals could have been either of two different possibilities, and therefore you have to remove one of those possibilities before you move up the way. Okay, I won't say any more on it than that because it's not vitally important for this module, but it is something that is there, and a lot of people would automatically assume, oh, well, the Gaussian isn't needed for smoothing there, but in actual fact it is. Okay, so we smooth with the Gaussian going in both directions. So just one point here, it works quite well as an interpolation method, and it also ensures that each pixel has the same impact as every other pixel. So, and again, I'm not going to go into detail on that, but the Gaussian is quite useful in terms of when you're doing that subsampling, it makes sure that no matter which direction you're going, every pixel plays an equal part in creating all the other pixels going the other direction. So so that no one pixel is treated as higher than the others in terms of the interpolation process. Of course, the separability, as I've already mentioned, one of the reasons the Gaussian pyramid is not excessively expensive to compute is that the Gaussian is separable. So in the case of reduction, this means that the image will be filtered and reduced on one axis, making a rectangular image, and then filtered and reduced on the other axis, bringing it back to square, but now at half the size in each axis, or a quarter of the area of the pixels of the original image. So this brings us on to another period called the Laplacian Pyramid, which is regularly used for image compression. And basically the idea here is that what you do is you take a Gaussian at one level, and you subtract from that an expansion of the Gaussian at the level above it. Okay, which is what we kind of said. So basically, you have the expand and the reduce there. So this GL plus 1 would originally been created by doing a reduce on GL, and then what we do is we expand it again, having gained no more information, and we subtract one from the other. So this can also be used to synthetically combine images. So if you've ever seen those where one image has been matted into another, this can be very useful for getting them in there so that down at very intricate little parts that it fits in well, rather than just looking like one thing pinned on top of another. And this brings us on to an approximation of that, which is called the difference of Gaussian pyramid. So an efficient way of calculating the Laplacian pyramid was introduced by Burton Edelson and was called the difference of Gaussians. It's only an approximation, but it's a good one and much more efficient to compute than the Laplacian. Now basically the idea here is that we take the original Laplacian of Gaussian here. This is a thing called the heat equation. So I'd say Niall would probably be a little bit more familiar with this. He might have come across it in his mechanical engineering. The rest of you may not have come across it. What we can do is we can basically get an approximate derivative there of this between two sigma values, and then when we play around with that, we come up with this here. Okay. Now this is an approximation in that this is the Laplacian of Gaussian. And this is done by basically a difference of two different Gaussians. Okay, so we have two different Gaussians, and this is our difference here, as you can see. The k-1 and the sigma squared are literally just a kind of a normalization that takes place on the Laplacian of Gaussian. So it actually turns out that they're quite useful rather than being a problem. This what looks different from the original approximation actually turns out to be somewhat useful. But more than that, I'm not going to go into any detail on it because it's a little bit beyond the scope of what we want to look at. The important thing from your point of view is that for a lot of these things, because some of these things are quite complex and to compute because they have a lot of computations in them, we're always trying to find an approximation that's pretty good and that also can be done quite efficiently. And so the difference of Gaussian turns out to be quite useful for that. So here's the difference of Gaussian pyramid, and the idea here is that what we do is we have an image and we take a second image here, and we do these with different. So if this was done with a sigma, this would be done by k sigma there, okay, where k is some value. So what we do is we have our original image here, and we have a Gaussian smoothed image. So it's smoothed by a different amount, and basically it's then just subtracted from that. So there's our subtraction there, and that gives us a difference of Gaussian. What we then do is we have something like k squared sigma there, and we subtract that from this one, and that gives us our next one, and so on. Okay, so these ones here have particular pieces of information in them that are quite useful because they're looking for things at different scales. So because we smooth at different scales, what we're going to do is we're going to find points that show up here at different scales, and that tells us something about the objects that are in there. Okay, so that's all I'm going to mention on pyramids for the moment. I'm going to finish this recording here, and then we're going to move on to SIFT, where you're going to see this diagram pop up again, but I just wanted to keep the pyramids as a separate recording. So